All right, let's do a couple examples to show you the difference between part one and part two of the fundamental theorem of calculus. So let's start with part one. Part one is going to be one where you're going to use derivative rules and finding derivatives and apply them to areas under the curve. So we're looking at our objects themselves being areas under the curve, something like this. And our task is to find an a derivative for the function big F. So we're going to learn to differentiate integrals. And to do this, the one thing we have to be careful of is what are we plugging into the bounds of integration? The fundamental theorem of calculus part one very simply says that the derivative is the function inside. The issue is here, we're not plugging x into the bound of the variable, we're plugging x squared, which means we're doing a composition of functions. The function x squared is literally plugged into the antiderivative formulation. So to do this, well, we're going to get our little f, our inside function, natural log. We can plug in x squared because x squared is being plugged in. But because this is a composition, the chain rule says we have to multiply by the derivative of the inside function. Since the derivative of x squared is 2x, we multiply it by 2x, and we get our actual derivative here. So it's not that tricky. It's just that if you haven't seen it before, you might be tempted to just stop at plugging in x squared and say, oh, I'm done. It's just what that function is. But you still need to do this extra step of multiplying by the derivative of the inside. So the big trap for derivatives is always the chain rule. Always look out for it. Say, is there something being plugged into something else? If there is, use the chain rule. If there isn't, you're safe and you can just proceed. For the fundamental theorem of calculus part two, we're this time going to find the integrals, that is the area under the curve, and we're going to do that by finding an antiderivative. So we're going to use power rules here. The antiderivative for 4x is going to be 2x squared, because we raise the power by 1 and divide by that power. The derivative of x squared is going to be x cubed, and we have to divide it by 3, because when we take the derivative here, the 3 comes down in front and they cancel. Now, to say that we have an antiderivative, but we haven't plugged in yet, the standard thing to do is this. We're going to put a vertical line. We're going to put the top bound on top, 4, and we're going to put the bottom boundary on the bottom, 0. This lets our reader know that we have not yet evaluated the area under the curve. We've only found the antiderivative, and then we promise next to plug in 4, and then plug in 0 and subtract the 2. So plug in 4, we're going to get 2 times 4 squared minus 4 cubed over 3. I'm going to put parentheses around it just so that I can see that this is the antiderivative where I've plugged in 4. And then I'm going to subtract where I plug in 0. And here I'm going to have 2 times 0 squared minus 0 cubed over 3. That's just going to be 0. So finishing off the evaluation, we get 2 times 16, that's 32, minus 4 cubed is 64 divided by 3. Yeah. So nothing too much to worry about. We can leave it at that, or we could put over a common denominator and subtract. Might as well do that. When we do, we're going to get 3 times 32 over 3 minus 64 over 3. 3 times 32 is going to be 64 plus another 32. 64 minus 64 is 0, so we'll just have 32 over 3 left over. So the area under the curve of 4x minus x squared between 0 and 4 is exactly 32/3. Notice that we get an exact number. We finally get our exact computations for areas under the curve. We don't have to take a limit anymore. We don't have to use approximation by Riemann sums. We can just use this fundamental theorem to actually compute the definite value for this integral. And this leads to all sorts of applications in physics, in economics, in every branch of science, and of course in mathematics itself. The next couple of weeks we're going to spend using this to compute volumes, to compute areas, to compute length of lines, all sorts of weird stuff, surface areas. So the applications you're going to see is what this particular course is mainly about. How do we apply different techniques to find antiderivatives so that we can use the fundamental theorem of calculus to get definite answers to real-world problems. All right, I'll see you in the next video.